So the third criteria, or the third criterion we are going to discuss today is called the Tresca. So the Tresca criterion is based on the philosophy of Tresca criterion is that the material would fail only when the shear is going to lead into failure. So there is no balance between, just not like Rankine. Rankine is only looking into the normal stresses. Tresca is only looking into shear. Mohr-Coulumb is looking into the balance between the normal and the shear. For Tresca, is only looking, just like Rankine is only looking at the maximum normal stress. Tresca is looking only at the maximum shear stress. So for Tresca, for the material to fail, the maximum shear stress would need to exceed a critical value. Okay, so this is Tresca philosophy. Only shear can lead into material failure. And as you know, the maximum shear is sigma 1 minus sigma 3 divided by 2. So this sigma 1 minus sigma 3 divided by 2 need to attain some critical number. So what is the critical number? Again, if you look into the uniaxial test, so the bar, the force applied to that, the stress tensor is going to lead into failure when sigma 1 is equal to sigma ultimate. Sorry. So this is going to be 0, 0, 0, 0, 0, 0, 0, 0. So once sigma ultimate will get into, once sigma 1 will get into sigma ultimate, the material is going to fail. We take this strain tensor, we use the Tresca criteria, we'll see that sigma ultimate, or sigma 1 minus 0 divided by 2 should be equal to sigma ultimate minus 0 divided by 2, and the critical number is going to be sigma ultimate divided by 2. We know failure is happening at sigma 1 equal to sigma ultimate. We put this information into the Tresca criteria. We'll see that the critical number, the failure, would happen at sigma ultimate divided by 2. So whenever this is equal to sigma ultimate divided by 2, then the material would fail. So the critical number, as I said, is sigma ultimate divided by 2. Tresca criterion is very relevant for ductile material. So we said Rankine is very useful for brittle material. For Mohr-Coulumb is very relevant for soil. Soil is brittle material. Tresca criterion is very relevant for ductile material. So for ductile material, you will be using sigma y, so the yield strength. So the yield stress is the critical number. So you compare to sigma y divided by 2. Okay. Now applying the criteria is straightforward. I'm going to solve one example, but before I solve one example, I want you to see certain failure pattern. Now, if you look into the uniaxial compressive stress test, and you have a bar or a concrete cylinder, and you apply the compressive strength, and you look into the failure pattern, you can see which cases would be relevant to which failure criteria. For example, if you observe this bad pattern, can you tell anything, or can you make any observation about the type of failure that has happened in this specific concrete cylinder? Do you have any observations or anything? Can you detect anything in this picture based on the type of failure? Have a look, and then I'm going to switch into the chat, and you tell me what you think. Now, if you look into this failure, you'll see that the failure is happening at some angle. Right? I mean, this is the critical angle. This is the plane where the maximum shear is happening, basically. I mean, I don't remember, or I don't know if you still remember the example we solved where we had the stress to be in this way. I think we had a number. Yes, I think we had 100 and 0, 100, 0, 0, 0, 0, 0. So I don't know if you still remember this example where we had 100 only in shear, and then we have to calculate the surface, or we had to calculate the principal stresses, the direction of the principal stresses, the principals, or the maximum shear stress, and the maximum shear stress was happening at a certain angle. It was 45 degrees. Now, the maximum principal stresses looked like this, I think. Minus 100, 0, 0, 0, 0. This is minus 100. And this is the type of case where you get only uniaxial forces. And if you remember, in this case, the plane where we had the shear, the maximum shear, it was 1 over square root of 2, 1 minus 1 and 0. And it was the one of the planes, and we had plus minus of that, and we also had minus and plus. And this is basically the 45 degrees. I mean, if this is 1 over square root of 2, 1 over square root of 2, then this angle here is 45 degrees. So if you look into this plane, you'll see that this plane is happening at pretty much a 45 degrees. And this is the plane where the maximum shear is happening. All right, see, the pattern of failure will happen according to the plane where you have the maximum shear. So it's not going to be the case that you are calculating any random plane. It is the plane where the shear force is going to achieve a maximum number, and you are trying to figure out where this plane is. So this plane is a physical plane. And the angle of this plane is physical, and when material is going to fail due to the shear, is going to fail at this specific plane. It's not going to fail at any other plane. It's going to fail exactly at this plane. So let us see another picture. And this is basically the plane of the failure. How about this one? Can you say anything about this material here? Case. So just like in the case of a uniaxial test, when you have the necking, I mean, when you apply the forces, you get a necking behavior. And this necking behavior is going to yield into the failure point. So the failure is going to happen at the necking phase. When you do the compressive stress test, instead of the necking, you have one section to become slightly fatter than the rest of the section. And you can start to see that this section here is slightly more fat. That is saying that the forces that is applied on this plane the force that is applied on this plane is leading into the cross section to expand. So basically the material is going to try and hold itself together, but it is not able to do that because of these normal stresses. So basically Jack is saying this is failing due to the normal stress, not the shear stress. So basically this is failing due to the normal stress. It's not failing because of the shear. And if you look into these cracks, more or less the cracks look vertical. I mean, it is not ideal vertical, but remember that this is also a three-dimensional photo. So if you look into the sample itself, you'll see that these cracks are pretty much parallel to the axis of the sample. And they are distributed across the entire surface. All right, one more observation about this picture. Will not deform to this extent. I mean, this deformation here are quite clear now, and this is quite obvious. If you go back to the previous sample where you had this brittle failure, and you remove the two pieces of concrete after the test and put them on top of each other, I mean, you just go back here and place these two pieces together and measure the dimension, you will see that the dimension would be pretty much exactly the same like before. Whereas in this case, the dimension would have changed significantly if you keep pushing up to the failure point and then you bring the pieces together, you'll see that the dimension had changed significantly. And this is because the material here is ductile, is not brittle. So the material is ductile, is quite soft, I would say, and the failure is happening because of the normal stress, is not happening because of the shear stress in this case. Now, the last picture, I think, in this, I'm going to discuss in this lecture. So the last picture, can you say anything about this one? I mean, it should be easier now to. Same like the previous case. So basically the failure is happening due to the normal stresses. And this is a brittle material compared to before we have a ductile material. So this is the same failure pattern. Again, if you look into the cracks, you'll see that the cracks are vertical, more or less, and happening across the entire surface. But this is a brittle material. To this sample here, I would probably use Tresca for that. For this case, probably Mohr-Coulumb or Rankine would make sense in this case. If you look into this one, Rankine would make a good sense in this case. So it is really up to the case or up to the situation they are going to design for. This is where you pick the design criteria. And as a designer, it's quite a critical decision to make on the failure that you want your material, on the failure of your material, how to expect the failure is going to happen. All right, so in this example, we have a problem here. Let us assume that we have a cube. And the stress state in this cube in principal directions is described as sigma 1, 0, 0, 0, sigma 2, 0, and 0, 0, sigma 3. And we are looking into the principal directions here. So this is sigma 1, sigma 2, and sigma 3. This is the largest, this is the smallest. Now, sigma, so according to Rankine criteria for this cube to fail, we have sigma 1 minus sigma 3 divided by 2 should be smaller than sigma y divided by 2. So basically, sigma 1 minus sigma 3 should be smaller than sigma y. This is according to Tresca. And assume that we have this. Since we are talking about the principal stresses, I'm just going to draw the stresses, sigma 1, sigma 2, and sigma 3. So this is basically the stresses. These are the faces where the stresses are active. And you don't have any shear stresses on this coordinate system because this is the principal directions coordinate system. Now, in this example here, we are assuming that this loading case is undergoing hydrostatic pressure case. Where is the hydrostatic pressure? All right, it's not on stresses, but it's going to be a hydrostatic pressure case. So assume that you have this cube here, and you add a very specific number to the stresses, but all these numbers are added on the same plane. So added to, I'll just make it smaller, shift it to this side. Added to, can you see the blue color? So I have some hydrostatic pressure. I'm going to explain in a minute why this is a hydrostatic pressure. So you basically are adding a pressure across all these directions, and this pressure is equal. So assume that you have a pressure equal to P, and this pressure is huge compared to the principal stresses, acting in the same normal directions, but is the same. So you apply P on this face, on this face, on this face, and of course, obviously, you have the same on the opposite faces also for equilibrium, but the equilibrium would also require that the sigma 1 is also applied in the opposite direction. I'm not drawing the opposite directions just for simplicity, but they exist. All right. Now, assume that you apply some extra pressure, P, on each one of these faces, and this P is equal. So it is exactly the same amount of P. Now, would this change the failure behavior? According to Tresca. So you look into the Tresca equation, you see that sigma 1 now is sigma 1 plus P. I'm going to put it in a different color. And sigma 3 also is sigma 3 plus P. So you're adding P to sigma 1 and you are adding P to sigma 3. If you look into the equation, this is exactly the same like before, and nothing would have changed. So this is still sigma 1 minus sigma 3, because you are just adding and subtracting P. Adding and subtracting P is not changing nothing, and P will not affect the failure. So if this is smaller than sigma y, this would remain smaller than sigma y. So I'll try to zoom slightly on that. Hopefully you can see it better. So you basically are adding the P to all the diagonal values. You are adding P to all the principal stresses, and this is equal forces or equal stress applied to each one of these faces. Oops. Now, if you look into the force P, I probably just use green. If you look into the force P that is applied here and here and here, this force P has absolutely no effect on the failure as long as it is applied in equal amounts on all the faces. Now, think about a case where you, look into the sigma 1, and sigma 1 would be probably in the range of 10 megapascal. On top of that, you add P, and then probably sigma 2 and sigma 3 are of the same order of magnitude. And then you look into P, and you add 1,000 megapascal. Adding 1,000 megapascal on top of this 10 megapascal is not making any difference at all. It's making absolutely no difference if you think about it. Now think about increasing P to 10 or 1 million megapascal, or probably 1 trillion megapascal, or 1,000 gigapascal, for example. This would make absolutely no difference at all, and the material would still has not failed, according to Tresca. Now, do you think this is a realistic behavior? If you look into tension, and you think that this is going to increase to probably 1,000 or 10,000 or 1 million megapascal, if it is tension, the material would certainly fail in tension. No. Now, this shear stress would not increase at all. The shear stress would remain the same amount of shear stress, but the material would fail due to the tension that would happen in the normal stress. Now, how about compression? How about instead of tension, I apply P in compression in all directions?